All right. Welcome everyone to the algorithms and software session, the first algorithms and software session of contributed talks for the Maple Conference 2024. We have 4 wonderful speakers for you on tap. Without further ado, I'd like to give the floor to Adam Gale for his talk entitled Partially Ordered Sets Package in Maple.
Okay, all right. So my name is Adam Gale. I am a third-year student at University of Western Ontario. So this is a Maple package specifically designed to handle partially ordered sets. I'd like to give some special thanks to Eric Postma for helping both teaching us to code in Maple and contributing a lot of the code for this. I'd like to thank Professor Marc Moreno Maza, who spearheaded the project, and the other members of the Orca Lab who also contributed. So partially ordered sets, what are they and why do we care? So what is a partially ordered set? A partially ordered set, or a post set, is a set of elements in combination with a binary relation. This binary relation describes how the elements in the set relate to each other. For partially ordered sets, this relation must satisfy 3 properties for all elements in the set. It must satisfy reflexivity, where every element is related to itself, antisymmetry, where if A relates to B and B relates to A, then A and B must be the same element, and transitivity. If A relates to B and B relates to C, then it follows that A relates to C as well. So the order must be consistent throughout the set. Unlike total orders, in a partially ordered set, not every pair of elements needs to be comparable. That is, for some A and B, neither A is related to B nor B is related to A. For our future examples, I'm going to be using the partially ordered set defined by the numbers 1 to 9 and the binary relation of divisibility. So I want to do a quick check to make sure that our post set fits this definition. For reflexivity, every number is obviously divisible by itself. This one is a freebie. For antisymmetry, there are no 2 elements that divide each other evenly. If 2 divides 4, 4 doesn't divide 2. 3 divides 6, 6 doesn't divide 3, and so on. And for transitivity, if A divides B, it must also divide all numbers that B divides. If 2 divides 4 and 4 divides 8, then it follows that 2 also divides 8. We can see that our example post set fits the definition, so let's continue. So what can we actually use these for? Partially ordered sets can be used to represent and tackle all sorts of problems, from concurrent computing and task scheduling to laying the groundwork for category theory. An example of the task scheduling model would be to have elements representing tasks and the binary relation being dependency. That would be if task A is related to task B, if task A must be finished before task B. After creating the model, you could use the topological sorting function to find the optimal order for task scheduling. You could also use the drawing function to generate a visual representation of the task schedule flow. So let's take a look at the actual Maple implementation of this package. So let's take a look at how we can actually build these post set objects. We can build our example post set that we discussed earlier, divisibility over 1 to 9, by calling the constructor with a set of elements and a binary relation. Here we're defining divisibility, defining our set of elements, and then using the constructor to form a post set object. Now that we've actually created the post set object, what exactly can we do with it? Well, let's see. The post set can be represented in a few different ways, so let's generate some formats that you may be familiar with. We can call the transitive closure, and we can call the transitive reduction to generate these matrices. The first matrix is the transitive closure representation that shows every relation that exists within the post set. The second matrix is a condensed structure, only showing relations that are not implied by the transitivity. Why do we care for having 2 different representations? Let's take a look. So we can actually draw 2 different graphs from this. We can draw the closure graph and we can draw the reduction graph. As you can see, the graph generated from the transitive reduction is more structured and easier for the end user to visually parse. So what else can we find out about these partially ordered sets? Now that we've created our post set object, let's take a look at some of the queries we can perform. Once again, for reference, we're going to be working with 1 to 9 over divisibility, and this is the poset that we're going to be referring to. We can ask for things like minimal or maximal elements, which are, with this custom drawing method, are visually obvious. So we can ask for the minimal elements of 1. We can see 1 up here. And we can ask for the maximal elements, in this case, 5, 6, 7, 8, 9. And we can see those visually represented here. We can also ask for the least and greatest elements of the entire poset. For some functions, we can actually tell the function what to return if the result would be empty. So if we ask for the least element, there's only one minimal element, so it ends up being 1. But there is no greatest element, as we have several maximal elements. In this case, we can actually tell the function what to return in that case. We just return the string, no greatest element found. We can also query the poset to find out if a chain exists between 2 elements. Here we're querying for a chain between 2 and 7 and 2 and 8. If we actually look at the graph, we can see there's no link between 2 and 7, and there is a chain between 2 and 8, so we get false and true. We can also ask what the greatest lower bound or least upper bound between elements is. Again, for smaller posets, our custom graph helps to visualize this. So we can ask for the greatest lower bound between 7 and 8. If we look at 7, we look at 8, and we see they're both connected via 1. So the function returns 1. We can choose 4, 6, and 8, and we can see that they are connected via 2. Similarly, we can check for least upper bounds as well. We can call it on 2 and 3 and see that they are connected via 6. And once again, we can see if there are elements that do not share any upper bounds, we can tell the function what to return in that case. In that case, we simply return no shared upper bound. We can ask if there is a chain of relations between a list of elements. In this case, the closure graph more closely aligns with the desired query. We can see we can ask if there's a chain between 1, 2, 4, and 8. In this case, we can obviously visually see 1, 2, 8. Same goes for 1, 2, and 8. But when we query for 1, 3, and 8, we can see that there is no connection of 1, 3, and 8, so we return false. We can determine whether or not a list of elements is an anti-chain. That is, there are no relations between any of the given elements. For 5, 7, and 9, well, these are all maximal elements, as we know, so there is no chain between them, so they are an anti-chain. But if we add 1 to that set, suddenly there are connections, and the answer is false. In fact, there are many attributes that we are able to derive once we have created this poset object in Maple. We can ask for the height of the poset. We can ask for some attributes of it. Is it graded? Is it ranked? Does it represent a lattice? We can ask for the rank of the poset, the rank of specific elements in the poset. And there's more not listed here as well. So there are other packages that we can use alongside this to actually sort of expand the power of this package. So as we mentioned earlier, partially ordered sets can be used to represent other objects, such as polyhedral sets. So let's take a look at how we can convert objects between these two formats. We'll use the polyhedral sets package to construct a 3-dimensional tetrahedron. So we've got this little guy here. This is a 3-dimensional tetrahedron. Once we have built this tetrahedron using polyhedral sets, we can transform these vertices, edges, and facets into elements of our partially ordered set. We'll take all of these elements and use the binary relation of inclusion to generate our poset. That is, a face would include any edges that construct it, an edge would include its vertices, and so on. So with that, we're creating our poset2 object. Now that we have a partially ordered set representation of a polyhedral set, we can use some commands from the poset package to get more information about the object. We can call minimal elements, maximal elements on it. In this case, the minimal elements are the vertices, and the maximal element is the element that represents the entire polyhedral set. What else can we do? Well, once again, we can use these commands to find attributes of the polyhedral set. We can find out whether it's graded, whether it's ranked, or whether it's a lattice. We're able to check for several special properties using these partially ordered set functions. We can also use the graph representation of the polyhedron. So right here, we can see the polyhedral set has been organized into layers. Our top layer represents the 6 vertices, the second row represents the 12 edges, the third row the 8 facets, and the final node the entire polyhedron. We can also view the polyhedral set's transitive closure, although it is considerably more difficult to glean meaningful information from. We can also generate the matrix representations of these objects. We can also use this to help visualize polyhedral sets of higher dimensions. Let's create a 4-dimensional polyhedral set. As you can see, we can't exactly plot a 4-dimensional polyhedral set. However, we can convert it to a partially ordered set and then use the graph representation to help us visualize the object. So our 4-dimensional object that can't be plotted can be turned into a partially ordered set, which can help us visualize the representation. So this is just one example of representing different objects as partially ordered sets. But it should give you a hint as to the kinds of manipulations this package is capable of in conjunction with other Maple. We also have a couple extra options for power users. Many functions have a built-in data validation, such as poset constructors testing for those 3 poset relations, reflexivity, antisymmetry, transitivity. Power users can supply optional arguments to some of these functions to skip this sometimes computationally expensive validation. Just don't blame me if something goes wrong after doing that. So if you want to mess around with this package, you want to play this package, you want to use it for something, you can actually find this on the Orca Labs GitHub page. We're going to continue to work on this. We're hoping to add some functionality, including generating partially ordered sets that are intervals of other larger partially ordered sets. We're working on a command to generate the Mobius function of the partially ordered set. And there are some actual improvements to the graphing as well. I think that's all I've got for you.
Thank you, Adam. That was a great talk. We have one question and time for one question. There is a question that is, can you detect the type of lattices?
I believe that is something we are still working on. I know we wanted to specify between like a face lattice representation of a polyhedral set and like just a lattice form. I believe that is not currently in the package, but it is something that is on our to-do list.
Thank you very much. That then brings us to the next talk by Aishat Olagunju, entitled Comprehensive LU Decomposition and True Path. If you could stop sharing, Adam, then we'll give Aishat the floor.
Thank you. Thank you. I'm Aishat Olagunju, a graduate student from the Department of Computer Science, Western University. And this project was done under the supervision of Professor Marc Moreno and Professor David Jeffrey. So there are parametric matrices that are of interest in practice, so it is natural to adapt linear algebra algorithms like LU decomposition, rank computation, Jordan canonical form, Hermite and Smith normal forms. An example can be found in the paper by Professor Rob Kors, where they explore the Hermite and Smith normal forms of this matrix, which models infectious disease vaccine effects. And then another can be found in the paper by Stephen Thornton, where they explore the Jordan canonical form of this 5x5 Cock-Murdoch matrix. So treating parameters as numbers is not sufficient for us. What that means is dealing with parameters by computing over the field of rational functions is not a satisfactory solution. Take, for example, this matrix with parameters A, B, and C. We decompose that into a permutation matrix P, a lower triangular matrix L, and an upper triangular matrix U. This is a generic solution for this matrix, but a user might want to specify values for A, B, and C for this decomposition. Just by glancing at it, If you specify B to be 2A, this yields a division by 0. So again, treating our parameters as numbers is not sufficient. So our objective is to take as input two things. First, an n by n matrix A over the field of parameters, and a list of polynomial constraint W over a set field. And to return a list of pairs, PQ, LU, P and Q representing the row and column permutation matrices, a lower triangular matrix L, and an upper triangular matrix U, with WI being a list of polynomial constraints on the field, and the condition A, which is PLUQ, holds with respect to the individual WIs, and the given constraint W is actually the disjoint union of the WIs. Case discussion. Now recall that the computations are performed with respect to a list W of polynomial constraints. We adapt non-parametric LU decomposition, in particular for pivot selection. When we consider a non-zero entry P as our pivot of A, should we ask whether P simplifies to 0 with respect to polynomial equations of W? To answer that question, let us consider P, which is x minus y as our pivot, and W, the given constraints with the polynomials. The polynomials of W, they form a Grobner basis of the ideal that they generate for x greater than y with respect to any term other. P does not reduce to 0 with respect to the polynomials of W, but P vanishes at x, y is equal to 1, 1, and minus 1, minus 1, which are actually the two solutions of W. So the answer to the question that we asked is no. It is not sufficient just to ask whether P simplifies to 0 with respect to the polynomial equations of W. What we should ask is, do P and W have common zeros? And this can be handled by the notion of a constructible set, which can be found in the regular chains library and the constructible set source library in Maple. What exactly is a constructible set? It is the solution set of a disjunction of conjunctions of polynomial equations and inequations. What that simply means is, for every constructible set C, you can compute regular systems, that is, systems with a triangular shape, so that your constructible set is actually the union of the zero sets of your regular systems. And given two constructible sets C1 and C2, you can deduce a regular system representation for their difference, their intersection, and their union. Switching over to the worksheet. So to show an example in the worksheet of how you construct a constructible set, you declare a polynomial ring R, and you construct a constructible set with a command general construct. Notice that our W has been slightly modified from the one in the slide, just to show points on which P vanishes and P doesn't vanish. We have multiplied that with X. So you compute that and it returns constructible sets. To view what is in that constructible set, you use the display command and you have this. And we construct our P also to be this. To find the common zeros, you use intersection and you have this. So P vanishes at this point and P doesn't vanish at this point. So what do we do for compressive LU? The steps that we take. We search for a non-zero pivot P in a column of A so that A has no common zeros with the given constraints W. If such a P is found, then we perform the row reduction step. Otherwise, we have two strategies. The first would be to keep searching for such a P pivot in other columns, or you accept a P so that P vanishes on some parts of W and doesn't vanish on the others. And those two strategies we call with pivot search with partial pivoting, CLU, and we have three cases for that. The first is a true path pivot was found, that is, the pivots we chose P has no common zeros with a given constraints W, which is the most ideal case. Or a pivot Q was found, but it wasn't a true path, so a split occurs. That means some parts of Q vanishes on W and some do not. And the third case would be no pivot was found. That is, W itself is actually a subset of the zero sets of that column. The other strategy would be to search for a true path in the whole matrix. So the first case would be a true path pivot was found in another column. That is no common zeros with the pivots and the given constraints, or no true pivot was found. That is, W is actually a subset of that column. If case 2 happens, then we fall back to the COU cases, that is the partial pivoting case. Experimentation. So we implemented this algorithm in Maple 2024 using an HP Pavilion with Windows 11. COU refers to comprehensive LU with partial pivoting, and FLU refers to comprehensive LU with full pivoting. To illustrate these methods, we have selected examples from various papers, and we ran these examples over the field of the parameters and an initially empty constructible set W, that is our given constraint. And we end up with this table where we compare the metrics for comprehensive LU with partial pivoting and full pivoting. At first glance, you can notice that at time, the computational time decreases with full pivoting. And as a result, we have less cases also when we use full pivoting. And our output reduces in size. So to show you an example on the worksheet, this matrix is from this paper cited above, and we define that matrix A, we construct our polynomial ring and the given constraints, which is initially empty. We compute the comprehensive LU with partial pivoting, and we display that. We end up with two cases, this first branch, and then this second. But if we give it full, this option, that is, we want it with full pivoting, we end up with one case, which says true. This is where we count the phrase true path, because there is actually a path that the LU decomposition can take such that we will not have splits when we consider our pivots, the case discussion. And it comes with the P and Q, so you know where swaps have taken place. Another example would be this Sylvester matrix, which we define, and we also define our polynomial ring and the given constraints. We compute the CRU decomposition, and we have 5 cases for that. With the full option, we also have 5 cases. But if we transpose that particular Sylvester matrix and we compute the comprehensive value with partial pivoting, we end up with 34 cases because we have limited the search in only the first column. But with full pivoting, we end up with 5 cases again, which is the initial one we started off with. Now, our work in progress is the optimization of a block matrix. This matrix we took from the book Chaotic Vibrations by Francis C. Moon, where M, at first glance, is the first block and the fourth block are the same matrix, and the second and the third are, in quotes, simple matrices, which is just the parameter multiplied by the identity matrix. So if we compute the comprehensive LU of that with partial pivoting, we end up with 54 cases. With full pivoting, we end up with 29. But with the block option, we have 15. Again, it's a work in progress. We're seeing if we can actually reduce this down to a more suitable option. So, conclusion. Our goal was to provide a procedure which comprehensively computes the LU decomposition of parametric matrices with constraints, and to offer heuristic methods with negligible overrides in an attempt to minimize the number of branches generated by the case discussion. And with our experimental results, we have been able to achieve some parts of our goal and reference it. Thank you.
Thank you very much, Aishat. That was a wonderful talk. I have one question. Do you have any thoughts about So what you've shown us is a great sort of a power tool, I think, for this. Do you have any thoughts about how to make this accessible for a non-expert user? Any ideas about user interface?
A user interface, yes. So we could have another option where it's like a pretty output option where it's more explainable, sort of the output. It's not just with the constructible sets. We are able to explain, oh, this and this is what happened with each step. That would all be a great option to have. And we're also thinking of also implementing the bar ice method. So we also have less cases for large matrices and also to try with sparse matrices to see if that would also reduce the number of cases also.
That's a great answer. Thank you.
Thank you.
Okay. I don't see any further questions in the chat, so I think we can move on to Álvaro Pereira Albert, who will be talking about dealing with non-principal locus in automatic reasoning in geometry.
So yes, thank you, Eric. Yeah, I'm going to be talking about how we can deal with non-principal locus when we're working with automated reasoning geometry. This is joint work with Tomás, Recio, and Pilar Vélez. So in this work, we work with GeoGebra, which is a dynamic geometry system software and it has both Jack and Tarski as embedded computer algebra systems. And these computer algebra systems allow us to develop several automatic reasoning tools, both in GeoGebra and in a fork version of GeoGebra called GeoGebra Discovery. And the main automatic reasoning tools are these 5: proof, relation, discover, show proof, and locus equation. My favorite one to tinker with is the discover one, which, given a geometrical construction and an element of that geometrical construction, it discovers any other elements in that construction and any relationships between the element you selected and those new ones that it discovers. But I'm going to focus on the locus equation command. So this equation, what it does, or what we want it to do, it is that we give it a geometric construction and a condition relating that construction, and a point of that construction that we can move, and the rest we take it as fixed. And we ask it to find the locus of points, so the set of points that satisfy that condition. So where can we put that movable point so that the construction satisfies the construction? If we translate the geometric construction into algebra, we can get a first algorithm to compute this. The geometric construction, we can translate it into an ideal of polynomials in many variables. We will see an example in a moment. The given condition is an additional polynomial, and then the point C is just the set of variables that appear, that need to appear in the condition, otherwise we wouldn't be doing anything. And that is going to be the point that we can move, and we expect an equation for the coordinates of C, such that if C satisfies those conditions, the condition that we wanted is also satisfied. And the way we do this is we get our ideal H that represents a geometric construction, we add the ideal P, and we eliminate all the variables except those that belong to the point C. So we only 2 variables if we're on the plane, or 3 variables if we're on the 3-dimensional space will remain. So let's look at an example. We have 2 points. Let's say A and B. A is the point -1, 0. B is the point 1, 0. And we are going to place a third point on the plane so that we're going to get a triangle ABC, and we want to know where can we put the plane C, so that's the Euler line of this triangle is perpendicular to the opposite side of the point C, so to the side AB. And we can ask GeoGebra to, or we can draw this in GeoGebra, so we get 3 points ABC, and A and B are going to be fixed, and C is the point that we're going to move. F and G are two different centers of this triangle. This line is the Euler line of the triangle ABC, and if we were in GeoGebra, we could move around the point C, and we could sort of come to the conclusion that C must lie in the perpendicular bisector of A and B. Since A is the point -1, 0 and B is the point 1, 0, then this perpendicular bisector is the y-axis. So we would expect that the condition, that the equation that must be satisfied is the equation x equals 0. However, when we input this into GeoGebra, we have, this is how the command is portrayed in GeoGebra Discovery. So we ask the locus equation for f and men to be perpendicular, and we move the point C, and we get a 5-degree polynomial, which is not what we expected. If we draw it, we find that at least part of the 0 set of this perpendicular of this 5-degree polynomial is the perpendicular bisector, but we get something else that a priori we don't know what it is. So the first thing we can do, we can copy this polynomial into Maple, and we can factor it, and we can see that the first factor in the factorization of this polynomial is the polynomial that we were looking for. And then we get two other polynomials, and each of these polynomials are degree 2 polynomials that represent 2 points. This is the polynomial x squared plus x plus 1 squared plus y squared. So its 0 set is just the point -1, 0, and this is x minus 1 squared plus y squared. So its 0 set is x plus 1, x minus 1, 0. Sorry, this is x plus. Sorry, its 0 set is 1, 0. And if we wanted to investigate even further, we could mirror what GeoGebra, the computations that GeoGebra does internally into with Maple. So we could, using the polynomials ideal package and the operators package, we could introduce this whole set of polynomial equations. So this is the polynomial ideal representing our construction, and in this ideal, v1, v2 are the coordinates of A, v3 and v4 for the coordinates of V, and v5 and v6 are the coordinates of C. And this equation here is the condition that we wanted to add. So if this is 0, then it means that the Euler line is perpendicular to the side through A and B. And then we eliminate all variables except those belonging to C, so that is B5 and B6, and we get this ideal here. And as we can see, this is not a principal ideal, so this is not an equation that we can draw, and this is why GeoGebra internally has some problems with it. But luckily, using Maple, we can explore this and see what happens. And if we look for the prime decomposition of this ideal, we get that it has 3 components. One of them, B5, is the one that we wanted. B5 equals 0, so x equals 0, and the other 2 are the are 2 points and are actually 2 degenerate points. This is the condition that A equals C, so we wouldn't have a triangle because 2 points would be equal. And this is the condition that B equals C, so again, we wouldn't have a triangle. So these are 2 degenerate components. And we see here, we look at the last 4 equations, we see that what we've done is we specialized the points in the beginning. So we said v1 to v-1, v2 to v0, etc. And Why did we do this? The first reason is a practical one, is that GeoGebra internally specializes all the points, and then if you change the input points, it computes everything again, so it is a practical one. The second reason is that it simplifies the computations. So in this case, we specialize for variables, and that effectively removes them from the computation, and we went from computing with 18 variables to computing with 14, which is a bit more manageable. And the third one is that it deletes several degeneracies automatically. Because if we hadn't specialized, for example, one degeneracy that would have appeared is the condition that A and B are the same point. In the moment we say that A is -1, 0 and B is 1, 0, that degeneracy cannot appear. And now, how can we deal with degeneracy conditions? In this example, we've seen that the degenerate components were 2 points, so were 0-dimensional, and the expected locus variety, the 0 set, was 1-dimensional. So we could just try to discard components of dimension lower than expected, but this doesn't work. We can see this example with this triangle is slightly different. Is centering, it has a vertex on 0, and if we ask, I'm not going to enter into much detail, but if we ask GeoGebra to find where can we put the third point of the triangle so that this equation is satisfied, the output of GeoGebra is a big polynomial, a degree 8 polynomial, and it cannot draw this polynomial. That's a first problem. And it also cannot factorize it. So we can again go to Maple and we can ask Maple to draw this polynomial using the Alcurves package. And we see that the 0 set, the real 0 set of this polynomial actually consists of only 4 points. So the 0, 0, the 1, 0, and these 2 other points. And the proper locus of the problem that we had is just these 2 points, which are the points for the triangle ABC to be an equilateral triangle, which is when that condition is satisfied. And again, 0, 0, and 1, 0 were the other 2 vertices of the example, so those are the degenerate components and have the exact same dimension as the locus that we wanted to find. So this could work in some examples, but not always. And some other 2 ideas that go hand in hand to deal with these degeneracy conditions. The first one would be to take the ideal H of the construction and then compute every component. So compute the primary decomposition of this component, and then for each primary component, if it is degenerate, we throw it away, and then for the non-degenerate ones, we add P. So we add the condition, and then we eliminate the variables that we need to eliminate. Or we can first eliminate the variables and then compute primary components, which is what we just did in this example. And this third idea is generally faster because again we eliminate first, so we presumably have less variables to work with when we want to compute the primary composition. And then to finish, open problems that we still have is the first is that computing both primary and primary decomposition is computationally very hard. So that is an obstacle to computing these things. The second one is that thing that we did about specializing the points actually restricts generalizing our results. And the third one is that unfortunately those 2 ideas, although the result is the same for both of them because these 2 operations actually commute, they don't find all the degeneracies. They only find degenerate components, but if we have some point that makes the construction not make sense, that makes this process doesn't find it. And that's all, and thanks for listening.
Thank you very much, Álvaro. I wanted to ask, you mentioned that the way that you sort of move the solution from GeoGebra into Maple is essentially by copy and paste. Is that right?
Yes, that is right.
Do you know, are there any extension APIs that it might be possible to use for GeoGebra so that we could make this an automated thing where you can programmatically move polynomials from one program to the other? Or
I don't really know about any APIs that could help us do it, either in GeoGebra and GeoGebra Discovery. What we do when we work with this is only in GeoGebra Discovery because it's sort of a developer's version of GeoGebra. We can actually access the internal logs of GeoGebra Discovery. And what we do when we try to solve this problem is we just select, copy, and paste into Maple.
Right, I see. Okay, yeah, thank you.
But that's definitely something to look into and to try to develop if possible.
I see one more question that came through in the chat, which is the following. Why did you start with GeoGebra and not do the whole work within Maple?
Because our original problem comes from trying to do this in GeoGebra.
Right.
We're trying to solve this problem in GeoGebra. We find results that are completely unexpected, and then we use Maple to explore these examples and try to see how can improve GeoGebra discovery and how can we work with this. And I just saw that Tomás answered your question, Eric. And in GeoGebra Discovery, there is the option to export to Maple.
That's wonderful. Great. Thank you for that.
Thank you.
Okay, with that, we move on to the last speaker of this session. Marcin Kaminski will present on integration of the relative Bhattacharyya entropy in Maple.
Ladies and gentlemen, dear members of Maple community, do you see my screen in Maple?
We see it, yes, thank you.
Yeah, fantastic. I came from a Department of Structural Mechanics. This is Faculty of Civil Engineering, Architecture, Environmental Engineering, so I'm not the computer scientist. This is Polish University, Łódź University of Technology, and we are using Maple since more than 20 years because of different books, different computer versions of the same software. So we are strongly associated to Maple solutions. And now, as it has been mentioned, I would like to tell you the few solutions and the few thoughts about determination of Bhattacharyya distance for two one-dimensional Gaussian distributions. This is the work in progress. Is a part of the research grant opus called Probabilistic Entropy in Engineering Computations, and this is sponsored by National Science Center, of course, located in Poland. The main idea is we are interested in probabilistic distance. Probabilistic distance is something that has not been implemented directly in Maple and is not easy available and computable in Maple, so it needs some special attention. And my goal would be to make some new functionality in Maple statistics library, because some colleagues of mine like to use this probabilistic distance to quantify the differences in between two populations, let's say. This is a very general applied science and engineering problem, and specifically in civil and mechanical engineering, this could be used for some reliability quantification. If you have, for instance, two different distributions, one of them would be called provisionally extreme value or extreme state of some engineering system, and the opposite would be admissible state of that system. We are not specifically interested in a difference in between two expectations of these two distributions, whose histograms have been, by the way, generated in Maple. We would be interested in some general measure. The truth is that not frequently we have for our disposal two Gaussian distributions. Usually one of them is Gaussian, the opposite rather not. Therefore, just simple quantification of a difference in between expectations is completely meaningless. I've taken, just for simplicity, what Wikipedia can tell you about different formulas. Usually the engineers are not interested in quantification or integration. They just would like to have simple formulas. So if you have, let's say, one-dimensional Gaussian distribution whose probability density function is widely known, and additionally you have two different Gaussian distributions, namely P1 and P2, this distance in between two different distributions can be expressed in terms of a difference of their mean values, as well as some more complex functions of their standard deviations, including some natural logarithm. Not frequently we have one-dimensional distributions. A more common situation is n-dimensional Gaussian distribution, and in this case we need to operate with some covariance matrices, which is much harder calculation. Nevertheless, if we would be unable to do that in one-dimensional case, multi-dimensional case is out of our, let's say, business. This formula is also available for some other probability distributions. Nevertheless, demonstration how to calculate analytically relative entropy is not so easy. And anyone who would like to check this fact falls usually into a situation that would like to define two different random variables, let's say x1, x2. Then to recall their probability distributions, which are normal, nevertheless, to make any analytical derivations, some assumptions considering non-negative character of standard deviations would be plausible. One may also assume that expectations are non-negative. And in this case, theoretically speaking, calculations should be successful. Nevertheless, it is not, because the classical formula for Bhattacharyya entropy, which means nothing else than a geometrical mean of a product of two different probability distributions, does not exist. It can be replaced with some other function, and calculation of some other function could be successful. And this success is seen here. So without square root, we can calculate their products with no further problems. Nevertheless, this is not convenient distance in between two different probability distributions. Okay, we can treat this problem from the first look in this way, that we have some analytical solution. So we have some algebraic equation, and without the proof, we can, let's say, implement it in some reliability analysis. Therefore, for some, let's say, illustration, what we could expect, we have random variable with normal distribution, and then we adopt some analytical function of this variable. This is linear transform, so relatively easy to check what would be the result. We also define the variation of this new random variable, and we can implement not only Bhattacharyya distance, but we can check it against well-known in engineering and applied science Kullback-Leibler distance. Nevertheless, Kullback-Leibler minority is that it is not symmetric with respect to a position of two distributions. So people use its symmetrization available as Jensen-Shannon relative entropy, and also for comparison, we consider Hellinger distance. These are not, let's say, very modern mathematical theories. Nevertheless, when we would like to make a comparison, Maple is very convenient, because this distance presented at the vertical axis could be calculated with respect to some input uncertainty measure. Therefore, we can, let's say, quantify a chaos in the difference in between two probability distributions. Now we skip from Maple to mathematics. So I'm gonna present some calculations, let's say in a mathematical analytical way. We are going to demonstrate how to calculate this geometrical mean for two different probability distributions. Before I will show you some calculations and transformations, I would like to say that it could be compiled in Maple, as you will see, but it is a little bit tricky, but still it has elementary algebraic transforms. Nevertheless, the problem is that thinking about computational implementations in Maple, there is no common methodology for various PDF types. So you need to make some kind of a table of the algorithms when the user may choose in between different distributions. So geometrical mean for two different Gaussian distributions is calculated under the assumption that we have two distributions with the expectations M1, M2, standard deviation sigma 1, sigma 2. The function for distribution is quite well known in mathematics. Nevertheless, we start from an introduction of the following function, which is nothing else than the power of this exponential function. We sum up two contributions from two different distributions. So we are trying to expand the form of this integral for further derivations. So practically speaking, we substitute for these two distributions under square root function. And then the function wx appears at the very end of this expansion. Now we are going to transform everything to the canonical form, and we apply some tricky substitution. This tricky substitution is not common for all pairs of different distributions. So we insert some inversion of standard deviations of both distributions. And the coefficients B and C, which are some algebraic combinations of probabilistic moments of these two distributions. Once we apply this notation, we can demonstrate that Wx equal to sum of two different contributions may be expressed as the function of the moments of these two distributions as S1 square x minus m1 square plus S2 square x minus m1 square. So we are going to express the last component in the above equation in terms of the first two moments of these PDF. Therefore, S squared C minus B squared equals at the very, very end as the combination of two second powers of standard deviations, so a product of variances, together with a square of a difference in between expectations, and it is scaled with summation of standard deviation. The summation of the standard deviation in square is similar to what we have in the formula, which can be seen in Wikipedia, for instance. Then one can apply the following simplification for Wx. This is not very difficult. We need to substitute for some new parameter d, which is nothing else than a product of standard deviation, a difference of expectation scaled over s. So finally, one may derive this geometric mean as the integral over some exponential function. I never tried if this exponential and its integral may be analytically integrated and evaluated to Maple. Nevertheless, it should be done with no further problems. So the last integral may be transformed to Poisson integral. So after simple algebra, we can arrive at the following expression. And this following expression is rather simple, elegant, and can be, let's say, implemented in the Maple system as some part of statistics library. Nevertheless, as I said at the very beginning, this is not quite straightforward, and I think the building of the entire library for probabilistic distance in between different distributions may be rather hard. We've demonstrated together with my father, who was for more than 40 years active mathematician in mathematics and computer science department, University of Nicolaus Copernicus in Torun, some more frequently applied pairs like geometric mean for two truncated Gaussian distributions, which is very, very important in the field of engineering, as well as geometric mean for two log-normal probability distributions. Usually these distances have very elegant mathematical form, but as I said at the very beginning, some substitutions are essentially different for different order of distributions. This is more or less I wanted to demonstrate as the, let's say, work in progress. Maybe till the next conference, Maple conference, I will be able to show you something more convincing in the system Maple. Thank you very much.
Thank you very much, Marcin. That was very interesting. I wanted to ask one question. I loved how you you found that tricky substitution involving the the various quantities relating the moments and stuff. I was wondering, is there an underlying insight? How do you find that substitution? Is that the sort of the main trick? It seemed like that was the hardest point, finding that.
Yes. Unfortunately, that is the hardest point. Unfortunately, because you cannot detect it by any computer algebra system. That's the pity. Usually, people are trying to make some numerical integration, etc., etc. So I'm going to tell you that they are trying to invent some general methodology. But in this case, general methodology fails because you have different pairs of totally different analytical functions, like for Poisson distribution, exponential distribution, extreme value distributions. They are similar in some way, but in details, these substitutions are not very important. One point is essential. Analytical substitutions do not increase numerical error, which is very important because people usually apply to this apparatus some finite element method or some other methodology where numerical error increases many times. So this, let's say, proposal is without numerical error.
Yes, that's a great point. Thank you for stating that.
Thank you very much.
Okay, with that, I'd like to thank Marcin and all of the speakers for this session.